Okay, so welcome back from the break. I hope it was all right. So clean filter. Is that going to go away? Let's see. Okay, good. So a couple of things I wanted to just remind you of before we get started. One is that we'll have assignment 3 due on Friday. And so at the same time, I'll return your graded assignment 2s. And then just by the end of today or before I wake up tomorrow, please do your lab number 4 sign up. Okay, so the kinds of things that we were talking about was this idea of propagation of error. And we were thinking about this problem where we're going to measure some quantities, say x1 plus or minus its uncertainty, x2 plus or minus its uncertainty, and so on. And maybe there's n quantities that we've measured. Then we want to go ahead and calculate something else using those measured values. So we calculate y as some function of all these things that we've measured, x1, x2, up to xn. And we want to know what is the corresponding uncertainty in that calculated value of y. And we went through this kind of argument where we imagined we have some function, it can have whatever shape you like, and at some particular value of x, we approximate that as a straight line. So we find the slope of some tangent line to the function at that point. And if there's some x interval that we're interested in that corresponds to, say, x plus or minus delta x or plus or minus sigma x, then we can find the corresponding y interval by taking the slope of that tangent line and multiplying it by that delta x. Okay, and we could do that for every one of our n parameters. And what we discovered is that we're going to calculate the uncertainty in y using this expression that involves derivatives of y with respect to x1, and then another term with a derivative with respect to x2, and so on up to xn. And so this is our general propagation of errors formula. So what I want to do is I want to do an example where we apply this. And the example that we're going to think about is from the Boltzmann's constant lab. So there, what you do is you measure some voltages and currents, you construct a certain plot that is linear. That plot has a slope m, and you find m and its uncertainty. It turns out that m is related to the electron charge divided by kb times T, where T is the temperature in units of Kelvin. And let's suppose we know temperature, like we measured it with just an alcohol thermometer or something like that. So we know the temperature plus or minus its uncertainty and the slope plus or minus its uncertainty. And maybe we know E from some other experiment. Maybe someone else has done a Millikan oil drop experiment and they measure the charge of an electron, E plus or minus sigma E. And our goal is to find Boltzmann's constant. So we can do that simply, just rearrange this so that Boltzmann's constant is E divided by the slope times temperature. And then we have to then calculate the uncertainty. Okay, so we want to find the uncertainty in Boltzmann's constant. And so we're going to apply propagation of errors. And I'll write out the full expression for this example. So the uncertainty in Boltzmann's constant, I'll write it out as the uncertainty squared of Boltzmann's constant is going to be the derivative of Boltzmann's constant, say with respect to the slope, times the uncertainty in the slope, and then we have to square it. And then we take the derivative with respect to, well, another one of our parameters was the temperature. And so we would have the derivative with respect to temperature times the uncertainty in the temperature squared. And then another possibility is that we have some uncertainty associated with the electron charge. So we have one final term that looks like this. And so that's all we have to do. Now it's just a matter of evaluating those derivatives. So we can do dkb dm is d by dm. And so let's see, Boltzmann's constant was the electron charge divided by the slope times temperature. I think, yeah. Okay, and so for this partial derivative, the charge and the temperature are assumed constant, and so we just have a derivative of 1 over the slope, and so that's minus 1 over the slope squared. So we have a 1 over the slope squared, and then the e and the t come along for the ride. I've written down the minus sign because, you know, that is the derivative, but it's going to turn out that for these propagation of error calculations, this kind of minus sign is not going to matter because it's going to go inside a square. And so it'll end up being a positive quantity. In any case, we can do the same sorts of calculations for the other variables, one being temperature. And that's going to be the same thing, except instead of an m squared in the denominator, we'll have a t squared. Okay, so it's going to be equal to minus e over m times t squared. And then we have to do the derivative with respect to the electron charge. That charge is in the numerator of our expression. And so this derivative is just 1 over slope times temperature. Okay, good. So all of these results are just going to be subbed into our propagation of error expression for these derivatives. So I guess should goes in for that derivative. And so when we make those substitutions, let's see, we're going to get the uncertainty in Boltzmann's constant squared is going to be equal to e over m squared times t times the uncertainty in m squared. I've dropped the minus sign because I know that a minus 1 squared is going to be plus 1. The second term is very similar. It's e over m, this time the temperature squared, and then we have the uncertainty in the temperature, square all of that. And then we have Boltzmann's constant. The derivative with respect to e is 1 over the slope times the temperature, and then we have to multiply by the uncertainty in the electron charge. Okay, and so all of these values are known, right? We've made measurements of each one of these constants. We've did a fit to get our slope and its uncertainty. So we know m and sigma m. We know, say, the electron charge from a different experiment. So we know sigma e. And the temperature we measure with a thermometer. So we know T, and we can estimate sigma T. Yeah.
Since if the second Boltzmann constant is a function of all those values,
yeah,
T can vary. Do we just plug in what we've measured at that certain?
Yeah. So for example, in the lab, we actually do measure Boltzmann's constant at 3 different temperatures: room temperature, ice water, and boiling water. So in that case, what you would do is you'd end up calculating 3 different values for Boltzmann's constant, and they'll each have a different uncertainty because, you know, for example, the room temperature measurement is probably the one where the temperature is the most stable. And so maybe its uncertainty, sigma T, is small compared to what it is for ice water or boiling water. Yeah. So you'd have to do this calculation 3 times. Well, in fact, you do the calculation once, but you're going to substitute in 3 sets of values. Yeah, that's right. Okay, so I want to make a couple comments about this. So first is we can just sub in our known / measured values to find the uncertainty in Boltzmann's constant. And so that's it. Some comments about this is, notice that we haven't made use of any of like kind of some of the rules that you're given in first year. So Boltzmann constant is E over M KB times T. Sorry, no, KB is E over M times T. So if you were to do this using like first year rules, what you would do is you'd say, okay, what I have to do is I have a quotient rule, but in the quotient I have a product. And so first I do product rule for that one, and then I do quotient rule for the others. And so you have to do all these little steps. What I like about this propagation of errors analysis is that you don't have to remember any rules. The only thing you have to remember is the general expression, and then you can just apply it. Okay, so there are no rules to remember. We just always apply the general propagation of errors expression. The other advantage is we were given rules for some functions like, you know, what if y was equal to the ln of x? What's the uncertainty in y? Well, first year didn't tell us the rule, so we don't know. But propagation of errors says, well, that's an easy thing to consider because I just take y, I take its derivative with respect to x. The derivative of ln x is 1 over x, multiplied by the uncertainty in x. And so the uncertainty in y is sigma x over x. So let's do that example. So propagation of errors works for any, let's say differentiable, I don't know how to spell that, differentiable function. So example, let's say y is equal to the ln of x. You could think of like blackbody radiation. You measure the intensity, and what you have to do is you have to take the ln of the intensity in your plots. So this is something that we encounter. So we measure x plus or minus sigma x, and the question is, what's sigma y? Okay, so by propagation of errors, we would say sigma y squared is going to be the derivative of y with respect to x times sigma x squared. Okay, for a function of one variable, I think we talked about this. I think a question was asked last time. We could just take the square root of both sides, and for functions of single variables, we could say sigma y is the derivative of y with respect to x times sigma x, and then just take the absolute value of everything. Okay, so for this case, the derivative of y with respect to x is d by dx of ln of x, which is 1 over x. And so that's going to go in there. And so sigma y is equal to the absolute value of sigma x over x. Okay, good. What I'd like to do is just quickly go back to the previous example with Boltzmann's constant. And I want to show that this gives a result that is consistent in some ways with the rules that you were given in first year. So let's see how that's going to work. If we did error analysis, our propagation of errors with say KB is, so what was it? E over M times T. Using the first year rules, we would, well, here we have either products or quotients, and the product quotient rule is the same. It's you add fractional errors, okay? We would do the following. We would say the uncertainty in Boltzmann's constant is equal to Boltzmann's constant, sorry. The uncertainty in Boltzmann's constant divided by Boltzmann's constant is equal to the uncertainty in E divided by E plus the uncertainty in M divided by M plus the uncertainty in T divided by T. Okay, so that's what we would do. If we solve for Boltzmann's constant, then we would find the following. It would be KB times, all these terms. But KB we could write as E over MT, and we're just going to distribute that through. So we would get the uncertainty in Boltzmann's constant is equal to, well, let's see. For the first term, this E is going to cancel with that 1 over E. So we would get sigma E over KBT plus. For the second, yeah, here it is. For the second term, we'd have a 1 over M times a 1 over M. So we would end up with E. What's that? Oh yeah, that's right. You are correct. Thank you. This should be an M, right? So this time we should get an M squared T, and then we would have the uncertainty in the slope. And then we should get a 1 over T times 1 over T. Good. So that should be E over M T squared sigma T. And so let's call this equation 2. And let's compare that to equation 1. The sigma M term is M squared over T. The sigma T term is M over T squared. The sigma E term is just M over T. And so all of these terms are the same in equations 1 and 2. The only difference is that we have a square around every term, then we add them up to get the square of the uncertainty. So equations 1 and 2 have the same terms. They differ only in the squares and square root. So the takeaway is that the first year rules were given to you as a way to get you to get the correct results that you obtain from derivatives. They've just made it simpler by saying you don't have to square and square root everything. In fact, what happens is this expression, equation 2, actually overestimates the uncertainty that equation 1 would get. So when you use equation 2, you'll always get a larger result than when you use equation 1. So the first year result, equation 2, overestimates the true uncertainty. Uncertainty given by equation 1. Okay, but other than the fact that we omit the squares and square roots, this result that we got is consistent with what we were told to do earlier in something like Physics 111 or with some equivalent course to that. Okay, good. Are there any other questions about this? Yeah.
Just generally, is the overestimation, kind of, it seems like in a way you're treating the second one as they're like vectors. You're doing.
Yeah, I mean, I think what happens is if you had. So when you just add uncertainties directly together, it's like saying that, okay, I've measured one quantity and I measured another, and if I sum those two, the first one, let's say I measure some distribution for some quantity x1, and so that's going to follow some Gaussian, and here's the average value of x1, and there'll be some standard deviation. Okay. Then I go and measure another quantity, x2, and so these are my x2 measurements. It follows some different distribution. There's some average value here and some standard deviation too. So if we wanted to find the distribution of x1 plus x2, we're going to get something like this. The average will sit right at the average of x1 plus the average of x2, but the width of this distribution will not be the width of sigma 1 and sigma 2, right? So this width, sigma total, or something like that, sigma total is less than sigma 1 plus sigma 2. And the reason it's less than that is because if you just add them directly, you're sort of assuming that when I've made x1 measurement, I'm typically going to be a standard deviation away from the average value. And when I make an x2 measurement, I'll typically be a standard deviation away. But it might be that for some of these measurements, I'm above the average, and over here I'm below. So when I add those two up, they self-compensate. And that's why this width is less than the sum of the two individuals. And it turns out that what happens is the square of sigma total is going to be equal to the square of sigma 1 and the square of sigma 2. And so that's why we do that kind of, it's called a quadrature sum. That's why we do it for our uncertainty analysis.
Is it just a coincidence that the equation for a circle?
No, it's not. It's because in the Gaussian probability distribution, so we're assuming these two follow Gaussian probabilities. We have the e to the x minus mu over sigma squared in the exponential. And so when you combine probabilities, you end up taking this product, and these products with these exponentials end up to. So I think that's where it comes from. Yeah. Okay, good. So let's then, what I want to do is I want to start thinking if we can come up with a way to formally figure out how to calculate the average. What's the best way to calculate the average? We all know the results. Like, let's say I measure some quantity n times. If I want to know the average, I just add up all the individual measurements and divide by n. We all take that for granted, but let's see if we could find out like where that actually comes from. Is there a rigorous way to formally derive how to best estimate the average of a set of measurements? So what we're going to try to do is determine how to best estimate the mean from a set of n measurements. Okay, so we're going to assume we've made n measurements of quantity x, and the data are Gaussian or normally distributed. So Gaussian distributed just means that there's equal probability of finding the result below or above the mean. It's a symmetric distribution. So it means the errors are completely random. Okay, so we know something about the Gaussian distribution, and so we can say that the probability that say measurement I, we're gonna do a sequence of measurements, x1, x2, x3, x4. So there's some measurement xi, I falls between 1 and 0. And so we suppose that this particular measurement falls between xi and xi plus dx. So we could ask the question, what is the probability that our measurement would fall in this range? Well, that probability is just given by the Gaussian distribution. It has a coefficient of 1 over sigma divided by it's times square root 2 pi, and then there's this exponential. There's a minus 1/2, and then it's x minus the mean divided by sigma squared. And then we have to have this dx, right? This dx is going to be the width of our rectangular area that we're trying to estimate. Okay, good. Now, one of the problems when you do a measurement like this is that we actually don't know the value of the mean ahead of time. Okay, so all we can do is come up with an estimate of the mean based on our measurements. And so we're going to try to determine what is the best way to estimate the true value of the mean mu. So mu is the mean of the parent distribution, which we don't know, right? To figure out the parent or the true distribution, you'd need an infinite number of measurements, and we can't possibly do that. So we usually don't know, the value of mu or its value ahead of time. So instead, our n measurements generate a sample distribution, right? So we take a sample of n points from this parent distribution, and we're going to try to extract as much information as we can from that sample distribution. So we generate a sample distribution with mean, I'm going to call it mu prime, and we estimate that the probability of measuring xi with, the probability of getting xi in trial I. So with trial I is the following. So we're just gonna write down this thing exactly. We're just gonna say, look, I don't actually know what the true mean is, so I'm gonna put in a mu prime, which is gonna be some estimate of the mean based on the data that we have. Okay, so pi will be the exact same expression, minus 1/2 xi. The only thing we're going to change is we're going to say we just have an estimate of what we think the mean might be. And then we just need our dx. Okay. So we could do this for any one of our n trials, right? There would be I equals 1, 2, 3, 4, 5, 6, all the way up to n. And we would have this probability each time where we just change the index from I to be 1, 2, 3, 4, and so on. So if I have all these individual probabilities, then what would the probability of measuring the value x1, and then x2, and then x3, and then x4, and so on? How would I combine probabilities to get the total probability of getting a particular data set? And we multiply them all, that's right. So the total probability of measuring x1 with trial 1, x2 with trial 2, xn with trial n is, so p, I'll write it as a p is a function of mu prime. It's just going to be probability 1 times probability 2 and all the way up to times probability n. Do you know, have you, like we have a notation for sums, right? The sigma. Do you know the notation for products? What's that? Yes, a capital pi, that's exactly right. So we can denote this as the product from I equals 1 to n of pi mu prime. Okay. So if we actually did this product, what we would end up with is, first of all, we have a coefficient 1 over sigma square root 2 pi. That's the same for every single probability. And so we're just going to multiply that n times. And so we would end up with a 1 over sigma square root 2 pi raised to the power n. And then we're going to get an exponential with like an x1 times an exponential with an x2 times an exponential with an x3. So what happens if I have a bunch of products of exponentials? What's that? Yeah, that's right. So we can combine all those exponentials into one, and then we would have a sum inside. So that would be equivalent to the exponential of, I'm going to move this over a little bit. Okay, so it would be the exponential of -1/2, and it would be the sum from I equals 1 to n. And what we're going to have in that sum is xi minus mu prime over sigma. And that has to be squared. And then we have to close our bracket. There we go. All right. Perfect. So, oh yeah, you're right. So there would be, sorry, the dx would be up here. You're right. I just missed it. It's in my notes. Good. Okay, so what are we going to do with this? First of all, we'll identify that this thing is just a constant with respect to mu prime. We're going to try to find out some information about this mu prime. And so I don't really care about the coefficient too much because it doesn't involve mu prime. The strategy is to use what's called the method of maximum likelihood. What we've done is we've calculated the probability of us measuring a particular data set. It's the probability that we measure x1 and then x2 and then x3 and then x4 and so on. And what we're going to assume is that the actual data set that we get is the one that is close to the values of x that would give us the maximum probability. So what we're going to do is we're going to say the method of maximum likelihood assumes that the actual data set and value of mu prime assumes that the actual data set and value of mu prime give the maximum value of p of mu prime. Okay, so how do you maximize functions? You take a derivative and do what? So you set it equal to 0. So we're going to try to find the value of mu prime that maximizes this probability. So we're going to take the derivative of p of mu prime set it equal to 0 and solve for mu prime. So we're going to evaluate dp of mu prime with respect to mu prime, set it equal to 0, solve for mu prime to find the value that maximizes p of mu prime. So that's what we want to do, and we could do exactly that. We're going to be slightly more clever than that. So instead of taking the derivative of the whole thing, if I want to maximize this result, what I could do is I could just minimize everything that's inside the exponential, ignoring the minus sign, right? Because mu prime doesn't affect the coefficient, so that coefficient, and it is what it is, nothing we can do to change that. What we can do is we can adjust mu prime to vary the argument of the exponential, and if we make the argument of the exponential as small as possible, then we get the biggest possible probability. So equivalently, we can minimize the quantity 1/2 sum I equals 1 to n of xi minus mu prime over sigma squared in the exponential to maximize p of mu prime. In fact, what I'm going to do is I'm going to call the stuff in the exponential without the minus sign, I'm going to call that just capital X. Okay, so our task then is to try to find dx d mu prime and set that equal to 0. So that's going to be d by d mu prime of 1/2 the sum I equals 1 to n of xi minus mu prime over sigma squared, like so. Okay, so the derivative can come inside the sum, right? As long as the sum doesn't involve mu prime, we can take that inside. So let's just do this first example. Let's slowly with as many steps as possible. So this is going to be d by d mu prime of xi minus mu prime over sigma squared, like that. Okay, so what is the derivative? What if I evaluate this derivative, what do I get? So okay, it's inside a square, so we're going to get a factor of 2, right? So this will be 1/2 the sum of I equals 1 to n. We'll get a factor of 2 from the square. And then we have to take the derivative of what's inside. So what's the derivative of the stuff inside the square with respect to mu prime? It's -1 over sigma, right? Okay. And so what we would end up with is the sigma is kind of a constant. So it's going to be squared, right? We could have taken the sigma squared out here and then just taken the derivative of xi minus mu prime squared. We would get -2 mu prime in that case. Okay, so this would end up being a 2 times xi minus mu prime. There's still going to be a sigma squared, and we're going to pick up a minus sign because there's a negative in front of this mu prime. Okay, so I think that's the result that we get, and then we want to set that equal to 0. Okay, so we have then distributing the sum. We'll cancel the two. We would have the sum of minus xi over sigma squared. So we'd have a minus 1 over sigma squared. The sum I equals 1 to n of xi. And then we would get a minus and a minus, it's going to be a plus. We'll get a mu prime over sigma squared, which are constant, so it'd be plus mu prime over sigma squared, sum of I equals 1 to n. And let's see, the 2 we canceled, the minus sign and the minus sign became a plus. We've dealt with the mu prime, we've dealt with the sigma squared. And so this sum is just acting on, just 1, right? We factored everything out of the sum, so all that's left is this 1. And all of that would have to be equal to 0. Okay. What does this sum evaluate to? It's just 1 plus 1 plus 1 plus 1 plus 1. Yeah, we're going to add 1 to itself n times, so that's just going to be an n. And the other thing we can do is we can say, look, both terms have a 1 over sigma squared. We can just multiply by sigma squared, 0 times sigma squared is still 0. And so we can cancel the sigma squareds. And what we're left with is minus sum of I equals 1 to n of xi plus mu prime over n is equal to 0. Sorry, not over n, it's times n, isn't it? It's mu prime times n is equal to 0. And all we do is solve for mu prime. Okay, so we'll take the sum over to this side, we'll divide by the n, and we get the familiar result. Mu prime is equal to 1 over n, sum of I equals 1 to n of xi. And so that is a derivation of a very intuitive and similar, like familiar result. This is the best estimate of the mean of a distribution based on a set of n measurements. So this is best estimate of the mean based off of n measurements. Okay, good. How are we doing time-wise? We have only a few minutes. So let me tell you what we're going to do next time on Friday. So, well, okay, let's do another thing. Let's have some fun. Okay, get ready, buckle up. So let's find the uncertainty in our estimate of the mean. Okay, so what we need to do is we need to find the uncertainty in mu prime when mu prime is a function of all of the individual measurements, right? It's a function of the x1 measurement, of the x2 measurement, and so on, up to xn. All right. Well, we know how to do that. We're going to apply propagation of errors. Propagation of errors says what we should do to find the square of the uncertainty in mu prime is take the derivative of mu prime with respect to every one of the individual measurements and then multiply it by the uncertainty of that measurement. Then we would square it, and then we would do d mu prime with dx2 sigma 2 squared. And we would do this for all n terms. Now, that looks like a bit of a mess, but we can simplify this. We could say, Well, if I took n measurements of the same quantity using the same method over and over again, I would expect all of the individual uncertainties to be the same. So if we repeat the same kind of measurement over and over, we expect sigma 1 is equal to sigma 2 is equal to sigma n, and we'll just call all of that sigma. So then sigma mu prime squared, the prime is on top of the mu, is going to be equal to sigma squared times all of these derivatives. And there would be n of these terms for our n measurements. Okay. So there's 3 minutes left, and that's perfect. All right, so let's think of this first derivative. So let's consider d by dx1 of mu prime. Well, that's d by dx1 of mu prime, we just said was 1 over n times the sum of I equals 1 to n of xi, which is going to be 1 over n times the derivative with respect to x1 of, well, the sum is just, it's just x1 plus x2 plus all the way up to xn. So what is the derivative of everything in this bracket? Does x2 depend on x1? So what's the derivative of that term? 0. All of these are going to be 0. What's this one? It's just going to be a 1. Okay. So this will just be a 1. And so therefore, this d mu prime dx1 is just equal to 1 times 1 over n. And so it's just going to be 1 over n. And if we did the same argument for any other of the derivatives, we would get the exact same result. Okay. So then we want to go back here and just say each one of these derivatives is a 1 over n. Okay, so that means sigma mu prime squared is equal to, we had a sigma squared out front, and then we had all these derivatives that were squared. And each one of those derivatives is going to be a 1 over n. How many terms are in this square brackets? N of them. So this is n times 1 over n squared. So this is sigma squared. This is n times 1 over n squared. And so that's equal to sigma squared over n. And lo and behold, therefore, sigma mu prime is equal to sigma over the square root of n. This is the standard error, or the error in the mean. Sigma is the standard deviation, or it's the uncertainty in any single measurement. And this is a result that we've used a bunch of times. We probably used it in first year without really truly understanding where it came from. But now that we have this propagation of errors tool, and now that we have like this rigorous derivation of where the mean comes from, we can use those two things to first say that, yes, the best estimate of the average is the sum of the measurements divided by the number of measurements. And the uncertainty, it's only an estimate, right? Because we'll never know the true value of the mean. It's only an estimate, so there's always going to be some uncertainty, and our propagation of errors tells us that uncertainty is the standard deviation divided by the square root of the number of trials. So our estimate of the mean gets better and better and better as we take more and more measurements, which is, I think, an intuitive result. However, the gains that you get less and less as n grows, right? So if you increase your n from 10 to 100, you get 10 times smaller uncertainty. But if you go from 100 to 200, then you're only going to reduce your uncertainty by a square root 2 factor. Okay, good. So that's a nice place to stop. What we'll think about on Friday is what happens if you want to combine measurements where all the uncertainties are not the same. What do you have to do? And so that'll lead to the so-called weighted mean and its uncertainty. All right, good. Thank you very much. And we'll see some of you in the lab.